Boom. Hello, everybody. Welcome to July 20th, last meeting. We're going to go over chapter 19 today. Any questions you have on previous stuff are also welcome. You can just raise your hand or pop it up in the chat, and I will answer it as things are going on. This is the last chapter of this unit. As you can see, the module is called Unit 6, 15, 16, and 19. Why do we jump over 17 and 18? It's because 17 and 18 are kind of more like each other than 15 and 19 are like each other, or 16 and 19, because acids kind of depend on concentration. And even though there is some equilibrium in there when it comes to acids, for the most part, it's more concentration than it is equilibrium. And so even though we're skipping 17 and 18, we just go right back to them. So some of the things that you might see if you're reading the book in chapter 19 will make more sense after chapter 17 and 18. So but for the sake of like the exam and like your classwork, we're going to do basic acid-based stuff, like what is an acid, what are the theories, strength of acid, strength of base, that kind of thing. It's just kind of understanding what that is, and then just really the concept of pH. So simple stuff. And again, if confused by what we're talking about today, then there is lots of videos on here that you can check out. These two are that Harvard series, so they're pretty good videos to watch. I recommend watching them. They have good series on the Annenberg Learner. Website. So as you can see, you have a good video, and then it just kind of walks through and it breaks down individual sections if you want. So yeah, pretty cool thing if you want to look at that. 25-minute video, not bad. Okay, so we can just jump right into acids and bases if you don't have any questions on chapter 15 or 16. Okay, let's just jump right in there then. So if we're using, my PowerPoints to take notes, that's fine. You don't have to. There's plenty of other good stuff out there. When it comes to acids and bases, we already kind of talked about what acids were, but just for the sake of conversation, acids are basically the most important industrial chemicals. Bases are pretty close as well. And the reason for that is most chemistry that we use to make our modern life is going to rely on an acid at some point, whether that's gasoline or plastics or computer chips. You're going to need an acid or a base in there to make those components. A great example of this is, I'm on a Surface Pro on here, and if I tilt it, the screen switches. Your phone does that same thing too, where you tilt the screen and it knows that you tilted it. Well, that's an accelerometer, and an accelerometer is a very tiny chip that requires a base to basically etch the circuit so that it can actually feel when it switches directions. So if we didn't have acids and bases or understood them, then we couldn't make things like accelerometers, and your phone would just be like any other TV screen. It was just one way, and if you turned it sideways, it wouldn't matter. But also because of the commonness of what acid and base is, because it basically comes from water, they're in everything. So I'm sitting here having some Diet Dr. Pepper, which is acidic, and most of my cleaners in my house are some sort of base, and then there's all kinds of other foods that we love that are, acidic. So let's just look at the properties of an acid or a base. Like, how do you know you're dealing with an acid or a base? So first off, feel. Now, for acids, they just feel like water. So it's kind of hard to feel that you're touching an acid, other than if you have like cuts on your fingers, they'll start to burn really quickly. But bases, though, are very obvious when you touch them. You will feel like your hand just got soapy. And the reason for that is um, they're very, very slippery because they break down fats and turn them into soap, essentially. So if you have oils on your hand and you're dealing with like a very weak base, you can kind of feel it's a little slippery. But if you're dealing with a strong base, it'll begin to break down those oils right away. You'll start to feel the soapy feeling. It can even start to break down the lipids in your cell walls. And so, bases are very, very dangerous. And so they feel slippery. So if you happen to get some chemicals on you and they feel like soap, they are not soap. They are probably a base. They are probably hurting you. You need to wash them off as soon as possible. And then taste. So again, we're not talking about, tasting strong acids and whatnot, but if you did, they would be horribly sour. But most of our foods that we like that are sour are acids. So most of the sodas that we like and the drinks that we like are probably going to be some sort of citric acid or phosphoric acid type drink. And those acids taste sour. And if you've ever had sour candy, most of the time the sour candy is just crystallized citric acid on the top of it. And some people have more of effect than others. So some people love sour candy and some people think it's gross. So there's other acids in there as well, but they're all what we call weak acid. Now, bitter foods, most people do not like bitter foods. When you taste something bitter like an unripe banana, you're just like, ew, this is gross. And the reason for that is bases are more damaging to cells than acids are. And so we have developed because we have stomach acid, we have hydrochloric acid in our stomachs, and so we're kind of accustomed to acids as just being the animals that we are. But bases, we don't like them, and so for humans, bases taste bitter, and we don't like them. There are very few exceptions. For instance, like dark chocolate is bitter, very weak base, but it's bitter, and we kind of like that flavor, but we still kind of add some things to it to kind of neutralize it. And then, of course, we have what's called litmus paper. Litmus paper is paper that's been coated with a chemical that, in the presence of an acid or a base, will change color. So you take blue litmus paper, and if you get it wet and it turns red, then it's an acid. And then you take red litmus paper, and if it turns blue, it's a base. But if nothing happens, then it's either an acid or neutral. So a lot of people say red acid. So some way to remember it. Because acids and bases are ionic compounds, they will form electrolytes. And so when we put an acid or a base in water, it will split up into its ions, usually hydrogen and hydroxide, but we'll talk about that in a second. And these will then make the water conductive. And so when we talk about strength of acid today, basically how conductive it is going to be the strength of the acid. So the more electrolyte properties it has, the stronger it is. So for instance, citric acid is an acid. It will taste sour, but if you pour the citric acid into the water and stir it up, it won't be as electrically conductive as if you put hydrochloric acid in there. So All right, so let's just get into the definitions of acid and base. So the first one we have here is Arrhenius. Arrhenius is the guy who actually discovers ions. So very important chemist. And Arrhenius discovers that he was playing with when you like burn things. You guys can try this if you want. You take a candle and then you snuff the candle out, and then the smoke will come up. And then if you take like an electromagnet, or if you have a like one of those ion chargers, you can like charge one side or the other. You'll notice that the smoke, if like say this is the positive end, this is the negative end, the smoke will start going like this. And that means that inside of that smoke, there must have been things with charge. So anyway, that's Arrhenius. He's one of the guys who discovers ions. He's the one who names them, cathode and anode and all that kind of stuff. And so what he says, okay, so the Arrhenius definition of an acid is any ionic compound where the cation equals H. So hydrogen cations are considered acids, and this is the Arrhenius definition. He then describes, we'll use Y. He then describes bases as hydroxides. So hydrogen ions. Sorry, that's a bad handwriting today. Hydrogen. And in this case, we have hydroxide as the anion. If you have hydroxide, you are a base. And the hydroxide ions are, like I said, they're bases. But why are we easier to deal with hydrogen ions than we are hydroxide ions? We use hydrogen ions for all kinds of things in our body. The electron transport chain uses hydrogen ions. The mitochondria uses a hydrogen ion gradient. Hydroxides, though, they love to come in and coax hydrogens off of things, and then they tend to, destroy them. So you want to make sure that you're being careful around bases. Even though we know acids are scary and we always think about acids, a lot of video games have like acid attacks in there. Bases would be pretty nasty too, especially on certain metals, and they're bad stuff. So anyway, that's Arrhenius' definition. Pretty simple. We have any sort of ionic compound with an H, or any kind of ionic compound that makes a hydroxide. And this describes like 90% of acids and bases. But there were still other compounds that were behaving in an acidic way or behaving in a basic way. And so there needed to be other definitions of acid and base. And so a guy by the name of Bronsted Lowry came in and he said, okay, rather than think about this in terms of hydroxide, because all hydroxides were bases, but there were some compounds that didn't have hydroxide in them that were acting like bases. And he came up with this idea of conjugate acid, conjugate base, and the idea of hydrogen donor, hydrogen acceptor. So what do we mean by that? Well, turns out that if you have something like hydrochloric acid, what are you doing? There we go. Hydrochloric acid. Hydrochloric acid is a gas. It is not a liquid. And if you have it and you put it in a chamber that's like water free, there's no water in there, it doesn't do a lot of acidic stuff. It just kind of, is a gas. It's when you add the water that you get what's called the dissociation. So they split apart. And this arrow right here means reversible, meaning it can happen one way, but it can also happen the other way. We'll talk more about that in chapter 18. But what happens is the hydrogen gets donated to the water, and the water accepts the hydrogen, and we're left with what's called the hydronium ion. Hydronium. The hydronium ion is water with an extra hydrogen on it. And you'll notice that it's positive, just like hydrogen ions by Arrhenius were thought to be the thing that causes acid. But what is in fact happening is this very reactive chemical is formed called hydronium, H3O+. And so with the Arrhenius definition of acids and bases, it was kind of hard to really understand strength of acid and strength of base. So in this case, Bronsted-Lowry is able to explain what's happening here. If this is our acid because it's our hydrogen donor, then water's acting like a base. You can think, well, wait a minute, where's hydroxide, right? Well, you can think of water like HOH, and then you can kind of see that there's hydroxide there. But you could also see that there's hydrogen there. That's why water is considered neutral. So these are what we call the acid and the base. Now, if we look at the reverse reaction, then this hydrogen will be given back to the chlorine. And so we call this our conjugate acid. Because it's the reverse acid. And this is what we call our conjugate base. And so when it came to acids and bases and kind of understanding what was going on, you could then start to look at the strength of the acid, like why is hydrochloric acid so much stronger than, say, acetic acid? Because if we looked at their reaction between water, where you get the formation of the hydronium ion, it was the strength of the conjugate base to get the hydrogen back that was causing the acid to be strong or weak. So in the case of, so here's our acid because it's our hydrogen donor. And here is our base because it's our hydrogen acceptor. And then now here's our conjugate acid. And so then here's our con base. And why? Because again, if we look at the reverse reaction, if we just look at it going backwards, then this H will go over here and we'll be making this and this. So in the case of the conjugate acid, they are the same, but it's the difference in the conjugate base. Chlorine ions exist because chlorine wanted an extra electron to become negative, and once it did that, it got its noble gas configuration and it's done. It doesn't care about anything else. So getting its hydrogen back is neither here nor there. There's other water molecules around. It can just go hang out with them. But right here, the acetate ion in the vinegar, acetate ion is got this big area over here. It looks like this. So here's our CH3 and here's our C double bond O and here's our O. This negative out here is completely exposed and it's completely unhappy. This oxygen is being fought by this oxygen for the electrons. And so getting its hydrogen back is going to be very, very easy for it. It's going to be able to take the hydrogen off of water very easily. And so we're going to get the reverse reaction in much higher concentration than in the first one, where the forward reaction is considered to be more prominent. So that's what we look at when we look at strengths of acids and bases. When Arrhenius, he was really just kind of saying like, well, The more H you have, then obviously the higher strength it is. But the big thing about Bronsted-Lowry was that it explained why some things were acting like bases even though they didn't have hydroxide. And the best example of this is ammonia. Ammonia is a base, but as you can see, it doesn't have hydroxide. Well, why is that? Because in this case, our base, ammonia, is going to get the hydrogen from the water. So the water is going to act as our acid because it's going to be a hydrogen donor. And what this makes is ammonium, which you guys have all heard about. And then guess what else it makes? Hydroxide. And as you can see, we now have a substance that's acting like a base because even though itself didn't have hydroxide, it produced hydroxide when it was reacting with water. Now, the strength of the base is just like the strength of the acid. We're going to look at the conjugate acid and we're going to look at the conjugate base. Again, thinking about acid and base in terms of proton donor, proton acceptor, to go in the backwards direction, this hydrogen is going to go back to the hydroxide to form water. And hydroxide is a very strong base. So we have a strong conjugate base. And so it's going to be able to take its hydrogen back. And we're going to go backwards more than we're going to go forwards. Okay. But it's still going to occur. And that's what causes ammonia to act like a base. You guys are very familiar with ammonia and ammonium because you've probably used Windex in your life. Windex has that unique smell because of the ammonia. But why do we put ammonia into Windex? Is because bases break down fats. And so grease and other kinds of nastiness that is on your windows for over time will be broken down by the Windex. Bugs, if you're cleaning your windshield on your car, the bug body parts can be broken down by the ammonia. That's why sometimes you want to spray it on there, kind of leave it for a second, and then wipe it off. So Bronsted-Lowry's definition is kind of all you really need to describe acids and bases. Describes like 99% of acids and bases. But in organic chemistry, we also have some substances that will behave like acids and bases, and they may not even have hydrogen. They may not even have hydroxide, and that is the Lewis theory. Lewis is Lewis dot structure, same guy. He comes up with electron pair acceptor, electron pair donor, and as you can see, they use the ammonia as an example of this. When the hydrogen ions are free, we can get what's called, the ammonia reaction. We're kind of missing the water, but again, this happens to happen in water. But we're not going to get too much into Lewis theory because it really kind of only deals with organic compounds. So we don't do a lot of organic in high school chemistry. But anyway, that's the idea, is that you can have electron pair donor, electron pair acceptor. So what do I mean by that? Well, remember that ammonia looks like this. And these out here are our electron pairs. So if the hydrogen comes in and it's a positive hydrogen, that means it has no electrons. So when it comes together with the ammonia, then we get the hydrogen coming in and borrowing those lone pair of electrons. Because that was our lone pair right there. And the hydrogen came in and just said, hey, I want to borrow your lone pair of electrons. And so the ammonia is a Lewis base because it was a electron pair donor. But this requires you to draw the dot structures. It's a lot of work, and it really only applies to a very few number of acids and bases that you won't come in contact with in your high school career. So when you see your textbook kind of going on and on about Lewis acids and Lewis bases, you can kind of skip over it. There's a couple things I'm going to tell you that it's like you don't really need to worry too much about. And I'll show you what I mean. If you look down here at the chapter 19 classwork, the one that doesn't have a number after it is just kind of the practice problems for every single section. And you can see here, it's like acid-base theories, and it kind of describes, Arrhenius and Bronsted-Lowry, but then you can see we have the Lewis acid. Is this a Lewis acid? Is this a Lewis base? You don't have to worry about that, so don't worry about that. We're not going to do any Lewis stuff. Okay. We talked a little bit about strengths of acids and bases. We'll talk a little bit more when we talk about pH. And we're going to do neutralization reactions, but we're not going to do salts. So, because sometimes salts can act like acids and bases, but it's confusing, so we're just not going to bother with it for these purposes. All right, so here's some terms real quick you might hear while you're reading your book or listening to a video. You'll have what's called monoprotic, and that's an acid that just has one hydrogen. And then you'll have polyprotic, and that's acids that have more than one hydrogen. A great example of this is the acids that have +2, +3 anion, or sorry, -2, -3 anions. So hydrochloric acid is what's called a monoprotic. And then, for instance, sulfuric acid is called a polyprotic because there's two hydrogens there. They both can act in an acidic way. And so we have the monoprotic acids, hydrochloric acid, and we have the polyprotic acids like sulfuric acid or like phosphoric acid, and so on and so forth. So that's what it means by protic. Because again, if we're talking about hydrogen, hydrogen's just H plus. That's why it's called protic, because it's basically a proton. And then this is kind of what the section 5 is talking about, which is what's called anhydrides, which is some sort of metal oxide, which when added to water becomes an acid or a base, but we're not going to really get into those, so don't have to worry about it. All right. So just to go out of order from the book a little bit, because I like to do neutralizations reactions before I talk about pH. So neutralization reactions are called that because basically we're going to have our acid, if we talk about Arrhenius acid-base neutralizations, we're going to have our acid react with our base. And they're called neutralization reactions because it's just a double replacement reaction where the H goes with the OH and the Y goes with the X. But it's called neutralization because it makes YX and it makes water. So the reason why it's called a neutralization is because we have our acid, we have our base, which are not neutral, and then we have our salt, and we have water. And when it comes to their pH, the water's pH, as you guys know from when you were younger, is 7. And so because the resulting pH, if you've mixed together the acid and base correctly, is 7, then we call that a neutralization reaction. Now, there could be super complex ones, but we're going to stick to really basic ones. The ones I ask you on the test are just basic Arrhenius acid-base neutralizations. So here's the most simple one. We have sodium hydroxide. We have hydrochloric acid. They switch partners, and we get literally salt, sodium chloride, and we get water. Acid-base neutralization reactions are really easy to balance. For every H, you need an OH. So if you have 1 and 1, then you're good. And then that's how many waters you have. So here's a good example. Say we have some sulfuric acid and we react that with potassium hydroxide. For every H, we need an OH, and we need to balance the charges of the salt. But when it comes to the actual balancing, well, for every H, we need an OH. There's 2 H's, there's only one of those, so we put a 2 there. Hey, that balances that out, and now we have 2 waters, so it's that simple. These are acid-base neutralizations. Okay, Arrhenius acid-base neutralizations. Bronsted-Lowry acid-base neutralizations, you'll see in the text. And again, if we're talking about Arrhenius acid and Arrhenius base, you might be talking about hydrochloric acid reacting with ammonia. Well, this obviously is not going to produce what you would expect in the other one, where we have nice, clean, no charges on everything. What's going to happen here is we're going to make ammonium and we're going to make chlorine, which will then have to be combined to make ammonium chloride. So they're a little bit more involved. And for your guys' purposes, you guys don't need to know about this stuff. Those of you who are thinking about AP chemistry, you can get into Arrhenius acid and base neutralization. But for our class, we're really just going to concentrate on Arrhenius. And then Lewis is the same thing, but again, we're not going to do Lewis. So yeah. So if you see any of that stuff in your text, you can just kind of skip over it. So that's the skeleton. You have your acid, so H and some sort of acid, and you have your base, Y and hydroxide there. And so here is our acid, here is our base, and the reason why it is called a neutralization is because it produces neutral salt, which in this case will be XY, and it produces water. So those are both neutral, salt and water. Just typed H2O again. All right, so that's an acid-base neutralization. Now, obviously, if you don't mix them together correctly, if you don't follow stoichiometry, then you will not completely neutralize it. And one way to monitor reactions is to monitor their pH. pH. So what does pH mean? Powers of hydrogen. And if for you math guys, does powers literally mean like powers, like 10 to the second? And the answer is yeah. pH is actually molarity. It's the molarity of the hydrogen concentration. So if there's a pH, there's also POH, because it's powers of hydroxide. Now, pH just caught on because most people, thought it sounded fun, and POH just didn't sound as cool as pH. Again, this is back in the day when they're doing this stuff. So PO is, considered rude to say. It means you smell. So that one didn't catch on as much. Or sorry, PU. PU is like considered you smell. So PO, PU, it's just kind of a weird way to say things. So that's where the P comes in. So what is P? P powers, okay, some hydrogen ion concentrations, like say for instance, hydrochloric acid, they're really high. So if you have 1 molar hydrochloric acid and you mix it together with water, you will get 1 mole of hydrogen ions, or 1 molar hydrogen ions. So you have 1 times 10 to the 0. And so this thing has a pH of 0. You notice the exponent is the pH. That's why it's powers of hydrogen. But if you have something like acetic acid, its reversible reaction will not produce very much hydrogen. And so you might have, if you have like, 1 molar of this, you might only have like 0.00, well, probably 0.001. And so if you rewrite this, this is 1 times 10 to the negative third, which gives you a pH of 3. Depends on the vinegar. Some vinegars pH can go down to like 2, or 1. But either way, that's what pH is. It means powers of hydrogen. And basically what it's trying to say is how good is the acid at becoming the hydronium ion. So pH is going to be equal to the powers of the hydrogen, but dropping all the numbers out to just have the exponent. And the way we do that in math is with logarithms. Whenever we use brackets like this, that means concentration. So they're talking, when you ever see brackets in chemistry like this, that means molarity or molality. In this case, we're talking about molarity. So it's going to be, LPHs are negative log of the concentration of the hydrogen ion, or the hydronium ion, depending on how you want to look at it. And POH is going to be the negative log of the hydroxide concentration. Now, why negative log? Because again, if we're talking about an acid and it has like 3.76 times 10 to the negative 5th molarity, to a regular person, that doesn't make any sense at all. They're just like, what is 3 times 10 to the negative 5th? And what's molarity? So to kind of help people understand the strength of acids and bases, they use that little trick of math to where you can remove all of this nastiness here and just kind of describe it in terms of the power, because the power is the thing that's the biggest part of this number. And that would be in a range. And that range could then tell people how strong an acid or how strong of a base it was, depending upon that range. Now, you guys probably know that pH, the pH scale, is equal to 0 to 14, with 7 in the middle. These guys are acids, and these guys are bases. So wait, why 14? What did they do to come up with 14? And I thought it was this like negative log thing. Well, let's take a look. I just said that this concentration here was acidic. And if we go over to our calculator and we do the calculation, we do negative log. Well, sometimes your calculator is a little bit annoying. So in the case of this, we usually have to type the number out. So 3.76 times, and I like to do this in parentheses. Parentheses, we got negative 5, 5 negative, and then we do 10x. There we go. And then we're going to end that in the parentheses. So we should have 3.76 times 10 to the negative 5th. And so there you go, you can see it. And then now we're going to do the log of that, and then we hit negative. It's still backwards to do it here on the computer's calculator. If you have a TI calculator, the TI-30X2 S, or if you have the TI-83 or a TI-84 or whatever, then it's more straightforward. You can just hit negative log and then type in what you need to type in, but I don't have that on the computer. So anyway, if we plug this math in, it tells us then that the pH is equal to 4.46. 4.3 actually. My bad. 4.3. And that's a lot easier for people to understand. You know, is this acid or is this base? It's on the acidic scale, right? It's on the acidic scale because it's less than 7. And it's not 0, so it's not crazy strong acid, but it's also not like 5 or 6. So, you know, it's probably decent. Everything we've talked about so far. We'll get there in a second. Just wanted to show you the pH scale. There we go. So as you can see, you know, if this is our pH scale, and these are super strong acids, and these are super strong bases, and it kind of falls right there. So it's not, you know, the weakest acid, but it's also not very strong at all. And so that's kind of what the pH scale was designed for, was to kind of give people an idea about like how strong they'd have to worry about this acid being. Because the understanding of powers was not really kind of a thing that most people did, but also, you know, shorthand. You want to draw things quicker and easier. If you're using a Prince's printing press back in the day, you want to use a lot less characters. Remember, this has 4 characters in it, this just has 1. So that was the idea behind using pH. Now, where does 14 come from? And the answer is what's called the self-ionization of water. So remember that Arrhenius said anything with H is an acid, anything with OH is a base. Well, if we rewrite this to look like this, then water is both acid and base. And then if we look at the Bronsted-Lowry definition, one of these waters can act like a hydrogen donor, and one of these things can act like a hydrogen acceptor. And what we can get is hydronium and hydroxide. So this is the self-ionization of water. Water will ionize itself. It will turn itself into hydronium and hydroxide. But, okay, it doesn't happen very often. If you watch the video, basically if you're looking at a swimming pool, you're looking at about 1 drop of that swimming pool being hydroxide and hydronium. So the reverse reaction is extremely highly favored. And when we talk about chapter 18, we'll talk about this in terms of what we call the equilibrium constant, where basically this thing is bouncing back and forth. Boop, 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 boop. But most everything is over here. Only a few things are going over here. And so the way that we describe that is we call it K, and we say that it's equal to the concentration of the products over the concentration of the reactants. It's a division problem. But water doesn't have concentration. It's not a solution. So in this case, when we're talking about water, which we call KEQ of water, it's just going to be the concentration of hydronium and the concentration of hydroxide, because we don't worry about the other 2 waters. And it just so happens that when we look at the self-ionization of water, water will ionize to be 1 times 10 to the -7th of both. So if we plug it into our equation here, water will then have a pH of the negative log of 10 to the -7, which if we plug that in will equal 7. And it will also have the negative log of 10 to the negative 7th of hydroxide, which if we plug that into the calculator, gives us 7. So the reason why water is considered neutral and 7 is considered a neutral pH is because you will always have some extremely tiny amount of hydronium and hydroxide because water will ionize itself. And so when you're looking at an acid or a base, you're looking at how much it pushes this equilibrium towards the H or the OH. If you add a bunch of base to water, the base is going to suck up all those hydrogen ions as they're being made. And so this will go down and this will go up. Sorry, this will go down and this will go up. And that's why the pH changes. Well, okay, where does the 14 then come in? You talked about all this stuff. Where's the 14 come? Well, basic math. What is 10 to the negative 7 times 10 to the negative 7? 10 to the negative 7 times 10 to the negative 7 is equal to what? That's right, 10 to the negative 14. So the scale goes from 0 to 14 because of the self-ionization of water. Acids and bases kind of need water to do their thing. And so the baseline is 7 because you'll have equal parts H and OH. And when you add the acid, it pushes it this way. And if you add the base, it pushes it that way. And then you have also what's called the pOH scale, which is just the reverse of that. So here's some handy dandy things for you to remember when doing your work. In the quiz or whatever, is pH is negative log of hydroxide concentration in molarity. pOH is negative log of hydroxide concentration in molarity. And then the concentration of hydrogen ions will be 10 to the negative pH. And the concentration of hydroxide will be 10 to the negative pOH. But let's say you just have pH, or say you just have hydroxide concentration, but they're interested in, hydrogen concentration, but they're interested in the hydroxide concentration, then the pH plus the pOH equals 14. So for instance, if you have a pH of 3, then the pOH has to be 11. Because together they will add up to 14. And vice versa. If you have a pOH of 3, then you have a pH of 11. And then if you're interested in what's the hydroxide concentration, the hydronium concentration or the hydroxide concentration, then this will just be 10 to the negative 3. And this will just be 10 to the negative 11. There's another one you can do. You can also do the KEQ is equal to the, or in this case, KEQ is 10 to the negative 14th. So 10 to the negative 14th is equal to the concentration of the hydroxide, or the hydronium, divided by the concentration of the hydroxide. But we're not going to do that one. Way too much annoying buttons in your calculator. But you can use that if you want. So if we look at your homework, it says, what is the pH of a solution? And it pops in this number right here. So let's go ahead and put that into our calculator. Now, right off the bat, you can just look at the power of hydrogen and say this said, it said, looking at this, what is this? Is this acid or base? And that 10 to the negative 9, you can just think of that as the, before we get the actual exact number, you can think of this as a pH of 9. And so this would be a base. And in this case, our pOH would be around 2. So that means our pH would be 12. And so this is probably an acid. You can just look at these numbers and figure out acid base from there. Well, let's go ahead and plug this into the calculator and tell them what the exact pH is. So if you're using the computer calculator, remember what you should do is you should start over here with the exponent, and you should do 9 negative, and then hit the 10x button, and that gives us 10 to the negative 9th. And now we're going to multiply that by 7.2, which gives us 7.2 times 10 to the negative 9th. And now we're going to hit the log button, and then we're going to hit the negative button. And now we get a pH of 8.14. And we said that this should probably be a basic, and a pH of 8 is just the very beginnings of being, noticeably basic. If this was not a strong base or a strong acid, then this might be something like the alkaline water that you buy at the store would be. And again, if the pH is 8.14, then we would just subtract 14 from that. So 14 minus 8.14. And while the pH is 8.14, the pOH is 5.86. So that's all they really want you to be able to do. And again, if you're having trouble with your calculator, let me know, and I'll try and show you how to use your calculator for that. But most of the questions I ask you on the test are questions like, classify acid, base, or neutral. So we have a 10 to the negative 9th. That's going to be a base, because remember, 10 to the 0 up to 10 to the negative 7 is our acid range. So this is going to be base. And then pOH and pH add up to 14. So if the pOH is 12, that means the pH is 2. And so that's an acid. And the same thing here. They're the opposite. So this would give us a pOH of around 11. So that means our pH is 3 or 2, depending on what this actually equals. And so this would probably be acid. And so really you can just look at the power of the hydrogen or the power of the hydroxide, which is exactly what the point of that was. So if you don't feel confident with your calculator, that's okay. We're going to do more of like question 4 here, where it's like, if the pH is 3.4, is that acid or base? Well, that's an acid. And then what would be the pOH? Well, you just 14 minus this number. On the quiz, there's a couple of these questions on here just to see if you can use your calculator. But on the test, I tend to stick to these types of questions. Because again, I'm trying to make it easy of access to everybody. When I'm in class, I tend to give you guys a calculator that can do it a very easily and clear way. So then I kind of focus on this a little bit more. But for the sake of this class, because we're all at home and we're all doing different calculators, and I can just assume that maybe you just have the Windows calculator, or I don't even know what the Mac calculator looks like. And as you can see, the Windows calculator is completely backwards in the way you have to do things. That's why I'm going to try and stick to just using the pH and the pOH scales for the math. So if we look at the thing, or the 19 section review, you'll notice it talks about strength or acids and bases. And so basically you can look at the strength of the acid in terms of pH. The lower the pH, the stronger the acid. Middle of the road pH, like the 2s and the 3s, you have weaker acids. But it's also really just the strength of the reverse reaction. Now there's a lot of questions on here about this, but really we're just interested in kind of understanding that strong acids and strong bases completely turn into H and OH, or whatever Bronsted-Lowry conjugate acid, conjugate base they have, where weak acids don't. And that's all you really need to know. You don't really need to get into looking at like, okay, what is the equilibrium expression and all that kind of stuff. we're not going to do that until chapter 18. So even though section 3 gets pretty heavy into it, we're just really interested in what is the definition of strong acid and strong base. Okay. Neutralization reactions are like I showed you, and I'm just about to show you like how to actually do these math on here with what's called titration, which is pretty simple. So I'll show you how to do that. And we're going to stick to what's called 1-to-1, but I'll also show you like 1-to-2 and other things like that. And then there's strong acid, strong base neutralizations and all that, but we're just going to stick to strong acid, weak base and all that, but we're just going to stick to the basic hydronium ones. So this is a little bit more advanced than needs to be. And if you guys look in modern chemistry textbooks, the acid-base chapter has been extremely reduced because most students, this is more than they need to know. So that's only most, it's all moved kind of into AP Chem. And the same thing for the salt solution, buffers and stuff like that. We're not going to talk about buffers at all, so you don't have to worry about that. So getting a little bit more into acid-base neutralization, I said that we can monitor acid-base neutralization by monitoring the pH. We're going to try and get the pH to 7. But how do we do the math to know that we've completely neutralized it? Well, say for instance, we have hydrochloric acid and we have sodium hydroxide, and we're going to mix those together and we're going to make sodium chloride and we're going to make water. Now we could just add them together until the pH was 7. And for that, we can use what's called indicators. You've played with indicators like pH paper, but there's also things like universal indicator. And if you've ever seen those commercials, like detergent commercials, where they'll like pour the soap into the pink solution and it makes the pink go away. That's an indicator of acid and base called phenolphthalein, which is kind of funny. But anyway, what we're going to do is we're going to mix these together and we're going to do what's called a titration to try and make them exactly 7. And the way we do that is we're going to have the molarity of the acid, say we have 1 mole, and we're going to have the volume of the acid, so molarity equals 1 molar, and our volume, say we have 50 milliliters of this. There's our volume. And now we want to know what the base's molarity was, and we dumped our 50 milliliters into 100 milliliters of the sodium hydroxide. And we noticed that it became neutral because we tested its pH and it said 7. So if we're trying to figure out what the molarity of this is, then what we can do is a very simple equation that looks very much like the dilution equation. The molarity of the acid, the volume of the acid, is equal to the molarity of the base times the volume of the base. And this is for 1-to-1 ratios. And what do I mean by that? 1 mole of acid to 1 mole of base. In this equation, they are 1-to-1. And if I ask you a question on the test, it's going to be a 1-to-1 titration type problem because they're very easy to solve. We have 1 molar hydrochloric acid. We have 50 milliliters of it. And we want to know what the molarity of the base is if it took us 100 milliliters to neutralize it. And so the molarity of the base will be equal to 1 molar times 50 milliliters divided by 100 milliliters. Yes, I'm on the black pen. Thank you. Thank you, sir. Black pen. All right, we'll write it over here. And you'll notice the molarity, or the milliliters cancel, and we're left with molarity, and 50 over 100 is 0.5, so this equals 0.5 molar. So our base was half as concentrated as our acid, and that's why it took twice as much volume to neutralize it. Those are titrations. So what about a titration that isn't 1-to-1? So say, for instance, we had some sulfuric acid, and we were reacting that with the sodium hydroxide. Well, this is going to turn into sodium sulfate, which is Na2SO4 and water. And to balance this, we're going to need to put a 2 here. So this is a 1-to-2 ratio. And so when we do a non-1-to-1, what we do is we take the molar coefficient of the acid and we put it over here on the base. So instead of it being molarity acid, volume of the acid equals molarity base, volume of the base, we're going to multiply this by the coefficient of the base. So we're going to say little b. And then we're going to multiply this by the coefficient of the acid, which is little a. And why does that make sense? Is because you are going to need to balance those out. And when you plug in the numbers, it cancels out to where the base doubling this is what accounts for the doubling of the base you need to react with it when we go to solve for whichever one we're solving for. A little bit more complicated. We're not going to do them. If you see them in like the worksheet here, if you look there, the very first one, we have to write the chemical reaction between sodium hydroxide and sulfuric acid. You'll notice that's a 1-to-2. And the same thing here. Here, I'll draw a snapshot. The first thing to do is to write the actual neutralization reaction. So in this case, it says we have some sulfuric acid, and we're going to react that with sodium hydroxide, and that will do exactly what we did on the other page, where it becomes sodium sulfate, and it becomes 2 water molecules. So that's a 1-to-2 ratio. So for this problem, we would want to go B times molarity A, volume A, is equal to A times molarity B, volume B. Well, A is 1, so we can ignore that, and then B is going to be 2, so we plug in a 2 there. And then it says, what is the molarity? So they want volume B, or molarity B, with 38 milliliters of solution. So this is 38 milliliters, and we have VB. A is 1, so we can ignore it. An endpoint with 14 milliliters of 75. So we have that, and we have 0.75 molar times 14 milliliters. So you can do this math however you want. You can move the 2 over here if you want, and then do VB, 38 times 2 is equal to the 0.75 molar times 14 liters. I need to move this since it won't let me right over there. But you guys are good at math, so you guys know what you're doing here. I'm sorry. Times 38 milliliters. So you can just move the 38 over here if you want. It's up to you how you do it. And see, that's where that 2 comes in. So it's not too much more difficult. It's just, I just wanted to give you the heads up that on the test, I'm just going to ask you 1-to-1. So you can kind of ignore that and just use the ones that I talked about. So a good example of a 1-to-1 is number 3 here. Number 3 is a 2 hydrogens and 2 hydroxides. So that one's really easy. You don't have to worry about the acid or the base. So basically we're just doing 1 through 4, and section 3 and section 4 we're doing at a much reduced rate. So you don't have to be worried about that too much. I don't know why I erased everything when I could just close it. All right, so that's it for today in terms of the chapter discussion. Be happy to answer any questions you have before we are done. Okay, guys, thanks for coming.